Okay, well, if you watch the page, internal page structure video first, you would have seen a number of general strategies for handling the handling the location of tuples within a page. If you want to find out the gory details of how Postgres does it, you can find in those directories. Each page is 8K bytes. And what is stored in that 8K bytes? Header information, the dictionary or the directory to the tuples, a free space region, and the actual tuples themselves inserted from the top down. So Postgres largely uses compacted free space, although it's not essential. And also we may have a region for storing things like index data. Large data values stored in separate files called toast files, which I'll talk about at the end. But that kind of storage is largely invisible to the functions that manipulate tuples. If you ask to extract a tuple and then ask for the fourth field, which happens to be a very large piece of text, you'll get the fourth field, and you get it in the same kind of way that you would have got the third field, which happens to be an integer. The underlying mechanism is clearly different, as we'll see, but at the interface level, the functions that implement access methods and so on just see that same thing. Give me the nth attribute. Alright, Postgres also supports blobs, binary large objects, which are an SQL standard thing for dealing with very large data items. And here they look different to the data items that you see. So they're a little bit more explicit than toasted stuff, which happens in the background, if you like. All right. So here's a Postgres page layout. And I can't remember whether this is offset 0. No, this may actually be the offset 8K. So the page header starts at the top of the page. Anyway, it doesn't matter, it starts at one end of the page. And then we have the directory, the offset flag's length for the tuples. So the location of each tuple is stored in the offset, and the length of the tuple is stored here. In the page structures that I looked at in the pages video, we didn't store the length explicitly in the directory, but we could have stored it inside the tuple as well. So the first couple of bytes of information in the tuple could be the length of the tuple, but in Postgres, the lengths are actually stored in the directory. All right, then we've got the free space region, and then we've got all of the tuples that have been inserted into the page. All right, so what is a page? Well, a page is defined to be a pointer. Basically, it's a char star, or more precisely, it might be an unsigned char star. So it's a pointer to a region of memory that is a byte buffer, if you like, 8K in size. All right, we just think of it as a page, though. Indexes into the tuple dictionary, so back up. So this is an array of triples. So the indexes into this array are 16 bit quantity. Even that seems quite large. I don't think we ever have 16 bits worth of location index. Anyway, you can have that many that many distinct index values for location. It's actually a byte making this into a byte, 8 bits would be too small. Making it into 16 bits is probably a bit generous. So maybe 12 bits would be useful. But you can't define 12-bit quantity directly like this. And then the entries in the tuple directory contain an offset, and this is, alright, so I've never seen these kind of definitions before. Here we're defining a bit string. So 15 bits of this unsigned int bit string, so it's going to be a 32-bit quantity. 15 bits are the offset from the start of the page. In other words, whereabouts in the page does the tuple live. Some flags that can tell you the status of the tuple and how long the tuple is, so another 15 bits. Even they sound slightly large for what we need. If we've got an 8K page, you don't need 15 bits to address that. I think, no you don't. So that's generous. Anyway, so 15 bits to tell us where the tuple's located, and another 15 bits to tell us how long the tuple is. So how many bytes starting at that offset location comprise the tuple data. Data types related to pages. We got things that'll tell us whether the page is full, for example, and we got the pointers to upper and lower, which we saw in the diagram, the offsets to the start and end of the free space, and various other information, including this tricky little definition here, which says the data, or the line pointer array, which is basically the information about each tuple, it seems to say that we've only got one entry in this array. Postgres uses this trick a lot. So it will define something like this, and then it will allocate some memory with this at the start of the memory, and then the rest of the memory will be used to hold the rest of this array, and the array can be as large as will fit in that memory. Right, so we can get an index into the page header data as well. All right, what kind of operations do we have on pages? Obviously, when we've got a brand new page, we need to initialize it. It'll set those values clearly and anything else to indicate empty page. We can add an item, where item effectively means record or tuple, to a page. So we can give the item itself, which is basically just a sequence of bytes, and we need to know how many bytes there are, so that information is also supplied, and we're inserting the item into a particular page. So it's going to try and allocate or find a free chunk of memory that size, put the item information into that space, and then set up the directory so it knows where the tuple was placed, and it returns the offset number. This operation can fail if there's not enough free space to store the tuple that we want to store. And here is where a function to do the compaction of the storage. So to merge all of those small fragments of free space into a single large free space. region. Postgres has basically got two different kinds of pages. Heap pages, which are the pages that contain tuples. I think I mentioned heap pages before. Nothing to do with the priority queue type heap. It's just a bunch of pages is effectively what that means, and index pages containing index entry. These things are qualitatively different. Heap pages containing tuples may have variable size entries in them. Index pages typically have entries that are much smaller than tuples and possibly fixed size. So we can play a few tricks with optimizing the usage of space in index pages. Having said that, they've basically both got the same layout, where you've got the header at the top, the directory, the free space, and then the entries in the page down the bottom. All right, so toasting. So I talked about oversized attributes in the section on pages. Here's what Postgres does. All right, so toast actually means the oversized attribute storage technique. Cute name. And basically what it's used for is to handle the storage of large attributes. Now, how do you define large? There's actually a tunable parameter where you can specify what large actually means. The default value is anything larger than 2K bytes is a candidate for toasting. You might say, how many attributes are going to be that long? Well, if you've got text, which happens to be a large piece of text, like a chapter of a book, that could certainly be larger than 2K bytes. Or if you've got something like a photo, an image file, then that's definitely going to be larger than 2K bytes. All right, so our data file looks like it did before. It's got tuple, 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 some tuples which happen to contain large attribute values have references to the toast file, and this is where the large values are actually stored. Okay, so large attribute values are stored outside the main data file. The value isn't actually stored in the attribute. What's actually stored in the attribute is a reference to toast data. So what Postgres can do, it can do compression on large values to, surprise, surprise, make them smaller. So they occupy less space when they're stored. Of course, if you're using compression to reduce the size of values, storage space becomes smaller. Potentially you need to read less pages in, but the downside is that you need to decompress them if you want to get access to the actual value. And that can be a relatively expensive operation, as can compression for that. Now, another thing that large attribute values aren't actually stored as a single long sequence of bytes. They're actually broken into 2K chunks. And the reason they do that is so that you don't have values that span multiple pages in the toast file. So you've got a chunk of data, another chunk of data, another chunk of data. Grab all of those chunks, put them together, and that'll give you a 6K chunk of possibly compressed large attribute data, which you can then reconstruct however you like, simply by concatenating, or maybe concatenating and then decompressing. All right, Postgres allows you to specify various strategies for dealing with large attribute values. So one of the strategies, plain, doesn't allow you to compress values of this column, doesn't allow you to do out-of-line storage. Basically what that means is you're not expecting any toastable values in that column. So it's something like an integer column or char 10 or whatever. It's never going to be a large, very large value that needs to be toasted. An extended value, defining a column as being extended storage type, basically means if you get very large values, you can compress them, and you can also store them outside. Now, if you compress a large value and it actually becomes small enough, then potentially you can store the compressed value in the tuple itself. But if you've got an extended thing, so you can compress values of that type and you can store them in a toast file. External means you can store them in a toast file, but you can't compress them. Why would you ever want to do that? Well, I kind of said before that maybe the cost of decompression is outweighed by the fact that not having to decompress things will be much faster. And obviously the counter to that is if you don't compress things and you store them, they take up more disk space. And you finally got another strategy which allows you to compress values but doesn't allow you to store them in a toast file. So like I said, if you've got values that you can compress down so that they're less than 2K, then you can actually store them in the data page rather than having to store them in a separate file. Now, of course, there's a cost to doing all this toasting, that you've got these large values stored in a separate file, which means if you want to access a tuple which has been toasted, you've got to read 2 pages. The page that contains the core tuple data plus the page that contains the out-of-line, possibly compressed data. But this seems to actually work quite well. If you're dealing with text data, they say that Postgres text data is just as fast as varchar data in a lot of other database systems. Alright, so Postgres page internals and toasting.